before. The problem statement here says we have a 2 kilogram block that is at rest on a smooth, frictionless surface. So that's something we need to take into account. And it is lying on a horizontal table. The length of the block is x, okay? A bullet of mass 0.015 kilogram traveling east, so it's going in the easterly direction at 400 meters per second, strikes the block and passes straight through it with constant acceleration. Refer to the diagram below and ignore any loss of mass of the bullet and the block. Right, so let's quickly look at the diagram over here. We've got the situation initially, that is before. The bullet is traveling at 400 meters per second in an easterly direction. We've got the 2 kilogram block of wood on a table that has a length of x meters, and it is stationary. Then afterwards the bullet has moved through the block, and now the block has a velocity of 0.7 meters per second also to the east, and the bullet has gone through the block and is keeping on moving afterwards also in an easterly direction. So obviously what happened in this situation is that the bullet has transferred some of its momentum to the block. So this problem is all about momentum. So let's move on and see what the first question is. They say here, state the principle of the conservation of linear momentum. Now, this is just a definition, and the definition for the principle of the conservation of linear momentum in words says the total linear momentum in a closed system is constant. Right, so let's unpack this statement. The total momentum in a closed system is constant. So that tells me that when I have a closed system, that means there is no external forces acting on the system. The total momentum before and after would be the same. And in this case, we've got a bullet and a block. So the total momentum of our system, which is the bullet and the block combined, is the same in the beginning as it is in the end, because in this case we've got no external forces acting on the system. And an example of an external force would be something like friction. So in this case we've been told we can ignore the effects of friction, so we can assume that this is a closed system. Just one more thing, another useful way to think of the conservation of linear momentum is to write it down in a mathematical form, and that is delta P is equal to 0, where P refers to momentum, and of course we can expand that to that the momentum in the end minus the momentum in the beginning is 0. Remember that we define a change in a physical quantity as the final quantity minus the initial quantity, and that gives me the change in linear momentum. Right, so let's move on and see how we can use this to solve the following question. Before we get to that, they also give us an additional piece of information. They say here the block moves eastward at 0.7 meters per second after the bullet has emerged from it. So we will take that into account when we solve the problem. Right, so first of all, let's again choose a reference or where we are measuring from. If we go back to the diagram, that was given to us in the problem statement, we see that all of the movement of this, within the system takes place in a linear or a straight line. So we are going to choose west as negative and east as positive. So that would be our choice of our system of reference. So west is negative and east is positive, and we will use that reference system to make sure that we have the correct signs for all of our quantities. Then, as always, it's useful to write down the given information. In this case, we've got the mass of the bullet, which is 0.015 kilograms. And just remember that we need to use SI units. So if they give you the mass of the bullet in grams, you need to turn it into kilograms. In this case, we don't need to do that. We also have the mass of the block, and I'm going to distinguish between the bullet and the block. For the bullet, I will use a lowercase b, and for the block, I will use an uppercase b. And we know that the mass of the block is 2 kilograms. We also are given the initial velocity of the bullet, which is moving at 400 meters per second. And remember, we've chosen east as positive, and the bullet is moving east, so we're going to make sure that we use a positive value for our initial velocity for the bullet. In the same manner, we also know what the initial velocity is for the block, and we can write that down as 0 meters per second because the block is at rest. And then the last piece of information that we are given is the velocity of the block after the bullet has moved through it, and we have a velocity of 0.7 meters per second, also in a positive direction, and that is all of the information that we've been given. If we go back to the question, they ask us to calculate the magnitude of the velocity of the bullet immediately after it emerges from the block. So the unknown in this case would be the velocity of the bullet after it has moved through the block. Right, so now that we've got everything together, let's see how we go about to solve this problem. Now remember, we said that the principle or the principle of the conservation of linear momentum tells us that the change in momentum is equal to 0, and as previously we said that Pf minus Pi is equal to 0, so I've just expanded that into the difference between the final and the initial amount of linear momentum. And then we can take this equation and rewrite it as that the momentum in the end is equal to the momentum in the beginning. So let's look at the initial amount of momentum. We can calculate that. Remember, initially we've got the bullet moving and the block is stationary. And if we look at the final situation, we've got both the block moving and the bullet continuing after it has moved through the block. So we will have to take that into account in both cases. So for the initial amount of momentum, for the bullet, we take its mass and multiply it by its velocity in the beginning. And we do the same for the block. We take its mass and multiply it by its initial velocity. There's two objects, so bullet and block. And we will do the same for the final amount of momentum. We take the mass of the bullet and multiply it by its final velocity. And we add the mass of the block multiplied by the velocity of the block, and now we've expanded this equation into that. Right, so that looks fairly complicated, but let's quickly look at what we have. We do have the mass of the bullet, we've got the mass of the block, we also have the initial velocity of the bullet as well as that of the block. We've got the mass of the bullet over here and the mass of the block over there, and we also have the final velocity of the block. So the only unknown in this equation is the velocity of the bullet after it has moved through the block, and that is exactly what we are asked to calculate in this question. So what we can do is we first of all substitute all of the known values into our equation, and we see that we only have one unknown, which is the velocity of the bullet in the end, this term over here, and we add the last term like so. So now we can solve for VBF, or the velocity of the bullet in the end, and we see that we get a value of 306.67 meters per second, and that is the velocity of the bullet in the end. And let's just quickly look at the value that we got. It kind of makes sense. Obviously, the bullet's velocity after it went through the block will be a lot less or smaller than before. And we can see that the bullet had a velocity of 400 meters per second before it hit the block. And after it's gone through, now it has a velocity of 306.67 meters per second. Right, so let's move on to the last part of this question. Question 4.3. They say here, if the bullet takes 0.02 seconds to travel through the block, calculate the length x of the block. So in this case, they give us an amount of time that the bullet takes to move through the block. So let's write that down as an additional piece of information that we are given. It takes 0.002 seconds for the bullet to move through the block, and in this case they want us now to calculate the length of the block. So how do we go about solving this problem? Now remember, when we talk about momentum, a change in momentum usually involves the change in the velocity of an object. So as I transfer momentum from one object, so in this case I have a bullet with a lot of momentum, and I transfer it, or some of that momentum, to the block as it moves through the block. And that transfer of momentum takes place over an amount of 0.002 seconds, and that is what we talk about when we talk about impulse. So remember, impulse, if we can quickly define impulse again. Impulse, remember, can be expressed as a net force acting over an amount of time. So the force here would be the bullet pushing on the block, and that is what creates, or that's what causes the transfer of momentum from the bullet to the block. It's the net force of the bullet pushing on the block, and that takes place over an amount of time, and that will then result in a change in momentum, and that is what we call impulse. So think about that. I can change the momentum of an object over a very short time. That means I will need to use a very big force if the time is very short. If, however, I want to create or to have a change in momentum over a longer period of time, then I only need to push with a smaller force. So that is the principle of momentum and impulse. So if we take that equation and we rewrite it as F net is equal to a change in momentum that takes place over an amount of time, we get that form of the impulse equation, and we can take that and we can expand it in the following way. Remember, a change in a physical quantity is defined as the final quantity. So in this case, it would be the final momentum minus the initial momentum, and we divide it by delta t. Right, so let's see what we can do now. Remember, momentum is equal to the mass of an object multiplied by its velocity. So we're going to expand these two terms to make use of that. So we get the net force acting on the block is equal to the final amount of momentum, which is equal to m times Vf minus m times Vi over delta t. Right, so we have F net is equal to m multiplied by Vf minus Vi, everything divided by delta t. So now we have the equation in a form where we can substitute the values for each of these physical quantities. So we've got F net is equal to the mass of the bullet, 0,015, multiplied by the difference between the final velocity and the initial velocity, which is 306,67 minus 400, and everything divided by 0,002. Right, so we use our calculators to calculate the net force which acts on the bullet, and we get negative 700,00 Newton. Now remember, we chose east as our positive direction, so we got a negative value here, and that kind of makes sense because the net force on the bullet is going to slow it down. So the bullet is moving in this way. The only way I can slow the bullet down is to pull on it this way, so that's why the net force on the bullet is negative 700 Newton. So now we can use that to calculate the length of the block. But remember, Newton's third law says that if something is pushing on one object, the other object is pushing with the same force that's equal in magnitude but opposite in direction. So that would be the net force on the bullet, and the net force on the block would be 700 Newton in the opposite direction. The one on the bullet is negative and the one on the block is positive. So we've got the net force acting on the block. So now the second part of the question is where we need to use the work kinetic energy theorem. So remember the work kinetic energy theorem, and remember we're going to apply this on the bullet. It says the net work done on an object is equal to the change in the kinetic energy of an object. So remember, kinetic energy is the energy of motion. If something is in motion, it has kinetic energy. So I am doing net work on an object when I'm changing the kinetic energy of an object. So remember, a positive change means something is getting bigger, a negative change means something is getting smaller, and zero means something has not changed. So a positive change in kinetic energy tells me I'm doing a positive amount of work. So we'll just keep that in mind when we solve the problem. So now the net work done, we can expand that. Remember, if I want to do or want to calculate the net work done on an object, I need to use the net force that is responsible for that change in work, and I can calculate it by taking the net force multiplied by the displacement multiplied by the cosine of the angle between the displacement and the net force. So if we think of our block, the block is moving in this way, the bullet is also moving from west to east, and the net force of the bullet pushing on the block is also in that direction. So in this case, F net is in the eastern direction as well as the displacement, or delta x. So this angle theta becomes 0. So when I take the cosine of an angle of 0 degrees, remember that that value is 1, so that will reduce further. But let's expand the kinetic energy further, or the change in kinetic energy further, as half m Vf squared minus Vi squared. And there we have expanded it. So now this equation simplifies to the following. F net times delta x is equal to half the mass times final velocity squared minus initial velocity squared. So there we have our work kinetic energy theorem for this situation. Right, so now what we need to do is we need to substitute the correct values. We've got the net force, we calculated that in the previous step. We want to calculate delta x. Remember the displacement over which the change in momentum takes place. We've got the mass of the bullet, and we also have the final and the initial velocities for the bullet. So we can substitute the values that we have for all of those as follows. We start with the net force as 700 Newton. We've got delta x, which is the unknown that we want to calculate, and that is all equal to half multiplied by the mass of the bullet, which is 0,015, multiplied by the final velocity of the bullet, which is 306,67 squared, minus 400 squared, which is the initial velocity of the bullet squared. And now we can calculate delta x because it's the only unknown in our equation, and we get a value of 0,71 meters, and that is the displacement of the bullet during the time which the change in momentum has taken place, and that would be the exact same length as of the block. So the result for this problem is 0.71 meters.